been raining beforehand, before it starts snowing, then it doesn't work great. But it worked good today, nice and dry. Okay, let's look at some announcements. You've got homework 3 due next Wednesday, and that's just 3 reservoirs. We're going to do another 3 reservoirs problem today using the Hazen-Williams equation. We're also going to talk about the fully turbulent flow assumption. It is another tool in our belt that helps us to overcome this issue we often face where we don't know the flow rate because we don't know the friction factor because we don't know the flow rate because we don't know the friction factor. You know, the chicken and the egg thing where we don't know exactly what to use as our starting F value. The fully turbulent flow assumption can be useful. So we'll do that, another 3 reservoirs example, and then we'll talk about how some of the equations we've used so far this semester apply to non-circular conduits, where we've talked about how the hydraulic radius for a circular conduit is just diameter divided by 4, but there's some other very simple modifications we can make when it's a rectangular or triangular or square conduit rather than circular. Okay, just a word about this coming summer. DOH is once again having their summer co-op program, so that if you don't already have something else lined up for this summer, you really ought to consider applying. They have opportunities spread all across the state, including at the headquarters in Charleston, some really neat, interesting work you could be doing. They have relatively relaxed eligibility requirements, and starting pay is better than you'd get at, working as a lifeguard or raking leaves at my house. So I'd encourage you to apply. The deadline is February 11th, so that's 2 weeks from today. All right. When you did homework 1, problem 7, you were required to use this diagram called the Moody diagram. You've seen it on several prior occasions. Some of you got the wrong answer, in part because you weren't as precise as you ought to have been when using the Moody diagram. Obviously there's a little bit of flexibility built in anytime you're using a graphical figure where you're running your finger over the page. I obviously have a little bit of tolerance for variation, but I wanted to illustrate that you can't be too sloppy, and especially because if you have a Darcy-Weisbach problem on the FE exam, you're not going to be solving the Colebrook equation on the FE exam. You probably won't even be using the Jane equation on the FE exam. If you have any problem using Darcy-Weisbach, they're going to have you refer to the Moody diagram to look up F. And so you'd need to be precise in using the Moody diagram, otherwise you get that question wrong. So we start in the Moody diagram with our relative roughness. And so let's say that we had a relative roughness of 0.002, like we did on that problem. So you follow this curve, which is highlighted now in red, and look for the intercept with whatever the applicable Reynolds number is. And for that problem it was 3 times 10 to the 4th. So here's 10 to the 4th, but do we go to the left or to the right? Well, this is 1 times 10 to the 4th. Here's 2 times 10 to the 4th, 3 times 10 to the 4th. So we go up and look for the point of intersection with our relative roughness curve. Okay, and then from there, you shoot over to the left and look for the intercept on the vertical axis on the left side of the figure. So the final step is going over to the side. So that's not 0.028. It's not 0.30. I mean, it's very clearly above 0.28, but it's not quite halfway. I think that what we could say is that the F value there is 0.0285, because it looks like it's about halfway between 0.28 and 0.29, maybe a little more than halfway potentially. Maybe I'd say 0.0286 if I was being cute about it, right? I mean, you can't tell with that much precision, but the main point is that it's not, 0.28 wouldn't be right. 0.285 would get you closer to the correct answer there. So please be sure to, get a good straight edge. Don't just use your finger as the straight edge when you're using the Moody diagram because the window of correct answers on the FE exam, they have these free, a lot of it's multiple choice. About half the problems are multiple choice, but about half of the problems are alternate item types, including some where you type in the answer. And they usually make the range of correct values a little bit narrower than you'd get right if you'd used 0.28 for this problem. Okay, so bottom line, just be accurate when you use the Moody diagram. It's never going to be as accurate as Colebrook or even Jane, but we can be as precise as possible. All right. So with that little soapbox lecture in our rearview mirror, let's talk about the fully turbulent flow assumption. If we assume that flow is fully turbulent, what we're effectively saying is, just for simplicity, let's assume that the water is going at a high velocity, and therefore the Reynolds number is really large. So let's think about why would that make our calculations a little bit easier if we just assume it's a big Reynolds number. So here's the Jane equation. Remember, the Jane equation takes into account the two factors that influence the friction factor. The first term in the Jane equation that's down here in the denominator within the logarithm, this first term is the relative roughness. The second term, which takes into account the Reynolds number, is having to do with flow conditions. So how is the F value different if the Reynolds number is really large? What does that do to the F value? If you have a very, very large Reynolds number, then what that does is it basically means you can neglect this second term. And in the chicken and the egg scenario, the whole thing that we've said we can't figure out is we can't figure out the F value because we don't know what's the flow rate yet. But if we assume that you've got a big Reynolds number, what this says is that the F value only depends on the relative roughness. So if you just look back over to the Moody diagram from here, there's a portion of the curve where the F value is only determined by the relative roughness, where you'd have the same F value if it's 10 to the 6th. If you have 10 to the 7th, the F value is the same. 4 times 10 to the 7th, the F value is the same. See how this curve is flat? This is the fully turbulent zone. In this figure, they're calling it the rough turbulent zone. That basically means there's a portion of the flow conditions where when you have a really high velocity, that doesn't impact the F value. If the velocity is really high, what determines the F value is the relative roughness. Okay, so this is a simplification, an assumption that we can use. Usually we apply it in the first round of iterations. You know, like if we're doing one of those spreadsheets where we have iteration 1, iteration 2, iteration 3, rather than just picking an F value from thin air for iteration 1, sometimes we'll use the fully turbulent flow assumption. And that's a better initial guess than just choosing an F value at random. It's a much better initial guess. And it will cause your solution to converge more quickly. If you're doing Excel, it doesn't matter so much if you're just doing copy and paste, you know, if you've got 3 iterations or 4 iterations. But occasionally there are a couple of things that we can't really set up on a spreadsheet. I'm thinking of one in particular that's called the loop method, where you're going to be doing your iterations on paper by hand. And it's really painful. You don't want to have any more iterations than you have to. So using the fully turbulent flow assumption for your first F value will in the end save you a lot of time compared to just like a random guess for your F value out of the gate. Okay, so that's the backstory of the fully turbulent flow assumption. The assumption is, let's neglect the effect of the Reynolds number just by assuming that you've got a high velocity. So then in your second iteration, you'd use the full Jane equation. You'd switch over. You'd only use this fully turbulent flow assumption in iteration 1. And then thereafter, you'd use an updated F value that's based on the actual flow conditions. Any questions about fully turbulent flow? Oh, okay. Well, the conclusion is you estimate the F value just by assuming that you're in this range where the Reynolds number change is not affecting the friction factor. Okay. 3 reservoirs. Who can refresh our memory? We talked about it on Wednesday. What's like the classical uncertainty of the three reservoirs problem? What is the main thing that we don't know? What makes this an ambiguous scenario? Go ahead.
Elevation at D.
The elevation at D. Okay. If we know the elevation at D, then then we can use it to calculate the pressure at D. That's definitely part of it. What else? What are we uncertain about when it comes to the flow rates and flow directions?
The flow in and out of A.
The flow in and out of A. And here A is the middle reservoir. That's exactly right. So we know that the water is going to flow out of the high reservoir. It's going to flow in to the low reservoir. But it's this middle reservoir. We don't know if the water is going to go in or out. So that whole process we went through on Wednesday was all about trying to figure out if the water is going to go in or out at A. And so what we did was we made a guess of how much head there was at D. So that is, how much energy is there at D? And once you have a guess or an assumption, then you can just say, well, if the head at D is bigger than the water surface elevation in the middle tank, then the water would flow from junction D towards the middle tank. And that's the process that we went through, is we made a guess, and then we found the corresponding F values and the corresponding V values. And then the way that we knew if our guess had to be raised or lowered is we had these criteria. If the flow in is too high, like if in is greater than out, then that told us to raise or lower our guess of D. So we knew that we could stop, that we didn't have to continue anymore once we had a guess F value that was within 2%. So we're looking for the F value to stabilize and then the flow in to equal the flow out. All right. So this process is even a little bit simpler if we use the Hazen-Williams equation, though. Because when we were doing it with Darcy-Weisbach, the tricky thing was the F values. The F value depends on the flow rate and so on. But here, if we have just fixed C values, then things will be simplified. So that template file that I provided online, if you haven't got that handy, you can go to Blackboard and find it in our course content at the bottom. It's this 3 reservoir problem spreadsheet example. So there was the first part of the question, which we already worked that example using Darcy-Weisbach equation. But the second tab is, let's look at the same question, but what if we use Hazen-Williams equation instead? So how is that going to make this simpler? Or, well, it's simpler. It's not more complicated. And look at these column titles across the top have been adjusted. It's not quite as much information. There's fewer steps because it's not an iterative process. We're having to recalculate the F value. We can just solve it directly. So let's go through this same example where we've got 120 feet for the top reservoir, 110 for the middle reservoir, and 70 feet for the lower reservoir. Now, in the previous example, we were using the Darcy-Weisbach equation, which is this, the one on the left, the Darcy-Weisbach equation. Hazen-Williams equation is a little bit different. We can still calculate the head loss or the flow velocity based on the slope of the energy grade line. So let's work through this together and just see how things are made different if we have a fixed C value rather than a variable F value. Okay, so pipe AD, pipe BD, pipe DC, and then we've got the materials. Has everybody got that same template file? Okay, I wanted to make sure that you had this second tab on the template file that I shared with you. Okay, let's key in the applicable C values for each of these pipes. For AD, it's a C value of 130, as it says in the image. For BD, it's also 130. And then this galvanized pipe, galvanized iron pipe from D to C is 120. You'll put in the lengths of the pipes, 750, 1,000, and 500. We'll put in the diameter of the pipe. Now, it's described in inches, but it's easier for us to calculate things if we record the diameter in feet. So we'll just do the quick conversion there. So AD is 8/12 of a foot. BD is 1 foot in diameter. And DC is again 8/12 of a foot. Okay. Calculate the cross-sectional area. Pi d squared divided by 4. All right. Now, we still do have to make a guess of the head D. And our first guess in the previous example was, let's say, 111 feet. So let's do that same guess as we had before, where we don't exactly know how much energy there is at D, but let's say, what if it's just slightly more energy than there is at A? And so then that will force the flow direction for our first iteration this way. Okay, so now this is the tricky part that I know sometimes students struggle on, is determining the head loss through the pipe. So we're saying that there's 111 feet of energy at D. So then that means if there's at B 120 and D 111, then the head loss from B towards D is going to be 120 minus 111. So that's 9 feet of head loss. BD, we would have the 111 minus the elevation of the water there is 110. Oh, I've done it backwards, haven't I? Yeah. I think I did the same thing last time too. A is this middle one. Okay, so A is 111 minus 110. Okay, tank B is the high one, so that's 120 minus how much head there is at D. And then finally the low one, reservoir C, is this head minus 70 feet. Any questions or concerns? Okay, the definition of S sub F is it's H sub F divided by the length of the pipe. So the slope of the energy grade line, S sub F, is going to be the head loss divided by the pipe length for each one of these. And we didn't have an S sub F term when we were doing this according to the Darcy-Weisbach equation because we didn't need it, but we will need it here. All right, so let's use the Hazen-Williams equation to calculate the flow velocity. 1.318 times the C sub H, that's C, times the hydraulic radius. Uh-oh, we don't have a column for hydraulic radius. Do you remember what's the formula of hydraulic radius for a circular pipe? D divided by 4. Right, so let me put a parenthesis here and we'll just refer to diameter divided by 4. And so then that will be to the power of 0.63 times the slope of the energy grade line. So I'll have to type this in, I-27. I can't click on it because my formula is now too wide. It's where I want to click. I-27 to the power of 0.54. Okay? So we've got some flow velocity. I can drag that formula down. I've got the flow velocity through each of the pipes. Okay, now this is where I say the in or the out, the flow direction. So right now, AD is out of the junction. BD is into the junction. And DC is out of the junction. Okay, the flow rates will be the velocity of flow multiplied by the cross-sectional area. So V times A is Q. We find the flow rate for all of them. And then down here below, in the next column to the right, we want to have all of the out minus the in. So there's two outflow terms. So we're going to have this top outflow plus pipe DC outflow, and then minus the inflow. So if continuity is honored, then in minus out will be 0, because we know there's no accumulation of water at D. D is just some enclosed junction. There's not a separate storage tank at D. So in equals out at junction D. But right now, our spreadsheet is not saying in equals out. It's saying that there's an imbalance. And so the conclusion there, out is bigger than in, so our guess of H sub D is too high. So since Q out is greater than Q in, well, greater than, I guess that's implied, Q in, then our guess of HD is too high. So let's lower it.
We started with an initial guess of the head at D is 111 feet. And what we can do is use goal seek in order to find what guess value of the head will lead to 0 error in terms of continuity equation. So I'll do data, what if analysis, goal seek, and my goal is for this cell to be equal to 0 by changing the guess of the head. And then I'll say okay, let it do the calculations, and in the end it is converging here on a guess head at D of 110.04 feet. So that would be the head at D that will give us flow in equal to flow out. And then I could go forward with the same process of calculating the pressure at junction D as was illustrated in the Darcy-Weisbach version of this example.
In the example on Wednesday, where we left was we had calculated the flow rates when we were doing the Darcy-Weisbach, but we hadn't yet calculated the pressure. And since that is something that you need to do on the homework assignment, let's skip back to the Darcy-Weisbach example, which is the one that worked from Wednesday, where we found the head values and the flow rates. And so part 2 of that example was finding the pressure at junction D. So does everybody have that part 2 from Wednesday's example? Okay, so these were the flow rates through each of the pipes, and we had calculated what the head at D is using this Darcy-Weisbach example. So in the template file, we've got a series of formulas where head is being defined as the pressure head, the elevation head, and the velocity head. And if you rearrange that, you can solve it for the pressure at D, which is what it's asking for in the second part of that example, is trying to determine what's the pressure at D. So the known head, which we calculated here in part 1, was 109.87. So if you just refer this cell up to iteration 4, where we had the value of H sub D determined. And I think in that earlier example, what we knew about the elevation at junction D is, let's see, did I give you a handout for that problem where it said that the elevation there was 85 feet?
It said that back when you were 84 slab on the bottom line.
Here, thank you. Yep, so the physical elevation of junction D is 85 feet. All right, so let's put in 85 feet for the Z value. And then you'll notice here when we rearrange the definition of head, we have to subtract out the velocity head. So the water is moving, and some of the energy that exists at D is in the velocity of the water. But what makes it a little bit complicated is which velocity would we use, because D is a junction of 3 different pipes. And so each one of them could have its own velocity. So I'll calculate the velocity head at each 3 of the pipes and then use the average of the 3 as the velocity head that we're going to assign to junction D. So you'll see here it says, what's the velocity in pipe AD? The velocity head. Velocity head is v squared divided by 2g. That's the velocity head. Okay, so velocity head at D is, here's the velocity in AD. So that squared divided by 2g, 32.2 for g. And then the velocity head in BD is the velocity through pipe BD squared divided by 2g. And the velocity head in DC is the velocity in DC squared divided by 2 times g. And then we'll just do the simple average of those 3. Okay, so we're going to assume that there's AD, let's see. Well, it's not actually 0, it's showing less precision. So the velocity head isn't itself 0, but if you're dividing it by 2 times 32.2, you're not seeing it if you're rounding it off to the nearest hundredth. But if you expand the digits, you'll see that it's not actually 0. Okay, so the velocity head at junction D. So we're going to have the pressure. We're going to use now this formula to calculate the pressure at D. So the pressure at D is the total head at D, that location, minus the Z at D, minus the average velocity head at D, and then all of that is multiplied by the unit weight of water, which in traditional units is 62.4. Okay, so we've got the pressure at D, and that's pounds per square foot, but if we wanted to know it in PSI, we would take the pounds per square foot and divide by 144. So 10.3 is the pressure there. All right, so at least now we've been through in the Darcy-Weisbach how we can determine the flow rates and with a known elevation find the pressure at junction D. When I get back to my office, I'll try and sort through the debris of this Hazen-Williams example, send you the solution to that, along with a description of why I was not able to get it here in class. But before we go our separate ways, let's just briefly talk about non-circular conduits and how we can handle the situation when, you know, it's not always going to be a circular pipe that water's flowing through. You can see that culverts are often non-circular in shape. Occasionally there may be square profile shapes that water's flowing through in tight spaces if you're trying to maximize the flow area. So if you have either of these cases, you wouldn't be able to use diameter. A lot of the equations we have, like Darcy-Weisbach equation, has diameter as one of the terms. So hydraulic radius, strictly speaking, isn't defined as diameter divided by 4. The actual definition of hydraulic radius is the area divided by the wetted perimeter. So you can calculate the hydraulic radius even for a non-circular conduit, and if you substitute in hydraulic radius times 4 in place of diameter, then we can use Darcy-Weisbach equation for a non-circular conduit. So you'll just notice that here where diameter would ordinarily go, we just make the substitution of the hydraulic radius times 4. And so Reynolds number is a similar thing. Normally, Reynolds number is velocity times diameter divided by kinematic viscosity. So if we're using the substitution that 4 times hydraulic radius goes in place of diameter, then Reynolds number would be velocity times 4 times hydraulic radius divided by kinematic viscosity, or if we're doing it in terms of absolute viscosity, it's what's shown on the slide there with density, velocity, 4 times hydraulic radius, and divided by the absolute viscosity. Relative roughness, which is usually K sub S divided by D, or epsilon divided by D, we just divide by 4 times the hydraulic radius in the denominator. So it's a relatively simple substitution for non-circular conduits. Just any place diameter used to be, put in 4 times the hydraulic radius. So if we have water that's going through a 12-meter long box culvert where we know the K sub S value, and here it's square in profile, 1.25 meters wide, 1.25 meters tall, and we have a flow rate of 0.4 cubic meters per second. Here I've substituted in all of the values. Instead of the diameter that we'd usually use, we can put in 4 times hydraulic radius. So for example, the Jane equation can be modified here in terms of 4 times the hydraulic radius instead of the diameter, the Reynolds number, and so on. So if we're going to make that substitution, let me just pull up the solution and show you the substitutions that would be used. Here it is. Okay, so you can see that we calculate the area, and with that area and the wetted perimeter for a non-circular conduit, let me just write this up on the board. The wetted perimeter is the distance all the way around. So we'd have the 1.25 plus another 1.25 and a third and a fourth. And so the wetted perimeter is 4 times, in this case, each side is 1.25 meters. So 5-meter wetted perimeter is what's dividing the area. So you get a hydraulic radius and substitute that hydraulic radius into the determination of the Reynolds number. And then here you can see in the Jane equation that the 4 times the hydraulic radius is going into the Jane equation. And let me just draw your attention to the fact that if, in this example, if we know the equivalent sand roughness in terms of millimeters, then we want to put millimeters as the length unit for hydraulic radius, because the units have to be the same. So in this substitution here, it's 1.6 millimeters of roughness and 312.5 millimeters of hydraulic radius. So it cancels out. This term itself is unitless, but the numerator and the denominator should both be in millimeters. Okay, and so making this substitution, there's not much head loss through this culvert. Relatively low flow rate means that there's going to be a very minimal head loss, especially because it's a really large culvert. But that's just an illustration of how you can make the substitutions for hydraulic radius when you've got a non-circular conduit.